Hello. Today we're going to be talking about a very unique theorem called the Lagrange interpolation formula, which basically says that if somebody gives you n points with all of the xi distinct, then there's a unique polynomial of degree less than or equal to n minus 1 that goes through all of them. And we can actually solve for this polynomial using this formula called the Lagrange interpolation formula, which we'll discuss in a little bit. So the first step of proving this theorem is actually just purely algebraic, and it involves proving the existence and uniqueness of the polynomial, unrelated to the formula itself. So let's go ahead and do that. So if I give you, so given x1, y1, xn, yn, where all the xi are distinct, we're asking, is there a polynomial that satisfies p of xi equals yi for all I? Okay, so if there was one of degree less than or equal to n minus 1, then we could write p of x in the form alpha, let's call it alpha 1 x to the n minus 1 plus alpha 2 x to the n minus 2 plus plus alpha n minus 1 x plus alpha n. Okay, so this is our polynomial. It has exactly n degrees of freedom corresponding to the n coefficients of the polynomial. And now plugging in the n points that we've been given into this polynomial, we get a set of n different equations. Okay, so for xi, yi, we have an equation which is p of xi, which is equal to alpha 1 x I n minus 1 plus plus alpha n is equal to yi. Okay, and we can write, all of these n equations in matrix form. Okay, so if I write them side by side, I have alpha 1 x1 to the n minus 1 plus alpha n, y1 alpha 1 x2 to the n minus 1 plus alpha n equals y2, etc. Okay, xn. And so we can recognize that we can rewrite this information in matrix form, okay? And take a second and think about what that matrix would look like. So that matrix is going to be of the form x1 to the n minus 1, x1 to the n minus 2, x1, 1, x2 to the n minus 1, x2 to the n minus 2, x2, 1, and all the way down to xn to the n minus 1, xn to the n minus 2, xn, 1. Okay, so it's an n by n matrix. And then the vector we're multiplying by is actually the vector of coefficients. Okay, so that's alpha 1, all the way down to alpha n. This is equal to our solution vector y1, y2, yn. Okay, so take a minute and look at this matrix form that I've written. These are ones, by the way. Sorry for my bad handwriting. And try and convince yourself that this indeed is a matrix form of these above equations. And when you verify that, recognize that in the matrix form, all of the unknowns, right, the coefficients are the only things that we don't know, that we're trying to solve for. They're all packaged in this vector here. And everything else has been given to us. We've been given all of the x1, y1, x2, y2, etc. Okay, so this equation is, I'm going to write it as a alpha is equal to y. We are simply asking, does this equation have a solution, and is this solution unique, where alpha is our solution? Okay, and so it turns out that in linear algebra, this equation can be answered by looking at the null space of the matrix A. So the null space is the set of all solutions to the equation A alpha equals 0. Okay. So if I set y equal to 0, I'm basically asking how many polynomials are there of the form p of xi equals 0 for all I. Okay. And if there was a polynomial that satisfied this, it would have to have n roots, right? Because there's n different xi. However, this polynomial is of degree n minus 1. And so there is no non-trivial polynomial of degree less than or equal to n minus 1 with n distinct roots. Okay? And this is something we know from studying polynomials over a field that that they can, even in the complex numbers, they can have at most as many roots as their degree. And so since we have a polynomial of degree n minus 1, it can never have more than n minus 1 roots unless it of course is identically 0. Okay? So then the only solution to A alpha equals 0 is alpha equals 0, which basically says that the null space is trivial. So null space of A is trivial. Now from linear algebra, we know that A is an n by n matrix, and if its null space is trivial, that means that A is a bidirection, right? So all of A is an invertible matrix. Its determinant is non-zero. All of its column vectors span the entire space Rn that we're dealing with here, or Cn. And so because the null space is trivial, we can figure out that indeed, okay, so thus the span of A is equal to Rn or Cn, and as a direct result, we know that the equation A alpha equals y has a unique solution. Namely, alpha equals A inverse y, right? Because A is invertible, because its null space is trivial. Okay, so that concludes the proof of the existence and uniqueness of such a polynomial. Okay, where again, the polynomial is the polynomial that satisfies these, that goes through each of these n points that we've been given. Okay, so now let's take a look at the Lagrange interpolation formula and see where this fits in. So this formula claims to provide this unique polynomial that we've just proved exists. Okay, so how does it do that? Well, this formula, if I plug in, I'll first just plug in the value of xi to see that the formula actually checks out and works, and then we'll kind of talk about why it works. So we need to check two things. The first, we need to check that first p of x is degree less than or equal to n minus 1. And secondly, that p of xi equals yi for all I. All right. So looking at this product here, the degree of p of x is going to only come from this x here. It's the only non-constant variable in this equation. And so we really just need to count the degree of x. And so we see that this product ranges over n minus 1 indices. Right? Because we're taking the product of every index for a fixed I, we're taking the product over j of every index not equal to I. So that would be exactly n minus 1 indices that are distinct from I. And in that case, we can see that indeed this x can have at most a degree of n minus 1, okay? So just by inspection, we could have terms that cancel, and so we could have something less than n minus 1. But this product term here can never exceed degree of n minus 1, okay? And so the first thing that we need to check is true by inspection. Now the second piece, which is the important part, is saying does P actually satisfy these initial conditions? And so if I plug in xi into P, I'm going to get the summation from I equals 1 to n. And now the indices are a bit confusing because, you know, I'm using I too many times. So let me write the index that we plug in as k, and that'll become apparent later. So if I plug in, you know, a specific point xk, yk, then I'm going to get the summation from I equals 1 to n of yk, and I'll erase this so y'all can see clearly, yk times the product of I not equal to j still, xk minus xj all over xi minus xj. Awesome. All right. So let's take a look at what happens here. So first thing I'll notice is that when this summation is ranging over I, okay, so when I is not equal to k, right, then one of these terms has to have a term that's k. So then j equals k in the product, right? Because we're producting over everything not equal to I. So if I is not k, then j is allowed to be k. And so one of these terms will be when j equals k. But when j equals k, we can see here that the top piece is going to go to 0. Okay, so we'll have x sub k minus x sub k in the product, basically. Excuse my notation, but we'll have this shows up in the product. And this term vanishes, right? X sub k minus x sub k, this goes to 0. So it turns out that when I doesn't equal k, this entire product is just 0. And that's by design, okay? So the product goes to 0. And then when I equals k, right? So that's the term in this, there's only one term in the summation that survives. And we have yk times the product of k not equal to j, x sub k minus x sub j over x sub I minus x sub j. Okay, and so what happens here? Let's see, this is very interesting. So notice I actually made a mistake here. So x sub I is gone now. Every I, we've chosen I equals k, and so this bottom term, x sub I minus x sub j, becomes x sub k minus x sub j. And so we see now that this product we have is identically 1. We're just multiplying 1 together n minus 1 times. So this is equal to 1. And so we're left with y sub k. Wow. So a lot of juggling indices around to give us ultimately what we were looking for, which is that this p of xk is equal to yk for all k, right? So let's go over this again. To summarize, if I plug in x sub k into this polynomial, then this summation, every term in this summation I'm summing over I, okay? And if I doesn't equal k, then one of these terms will be 0 because k gets included in this product, okay? And so the only term that survives is when I equals k. This is the only non-zero term in the sum that survives. And when I equals k, then I'm going to have y sub k times the product of a bunch of fractions that are just x sub k minus x sub j over x sub k minus x sub j. And so it just goes to 1, and I'm left with y sub k. All right, so it seems to kind of magically work. Like we get a bunch of cancellations in the perfect way, and p of xk equals y of k, and voila, we have our polynomial that we've desired. But why does this work? So where did Lagrange, I believe, come up with this formula, right? So let's discuss that. Well, there's two parts of it. Okay, so the first part is this formula. Let's paste it again here. So we'll notice that there are n polynomials, and the polynomials are y sub I, product of I not equal to j, x minus x sub j over x sub I minus x sub j. And they're each of degree n minus 1. And these polynomials have the property that that basically when you plug in x sub k, so we can call these polynomials maybe qi. So when I plug in x sub k, then either I'm going to get 0, so this term goes to 0, this product, or I get exactly y sub k. And this is for when I is not equal to k, and this is for when I equals k, right? So we construct a polynomial where this term, this polynomial, is either, it has n minus 1 roots. Those roots are exactly all these x sub j's that aren't equal to I, okay? So those are n minus 1 roots is precisely when I not equal to k. That's where this numerator comes from. And then the denominator ensures that when I equals k, then we just get then I get x sub I, or you can call it x sub k minus x sub j over x sub k minus x sub j. And so this denominator normalizes the polynomial when it's non-zero, so that this thing goes to 1. And when it goes to 1, we're just left with the surviving term y sub I. All right. So how does this work? Each polynomial has n minus 1 roots, q sub I, which are exactly x sub j not equal to x sub I. Okay, and so this is where the product of x minus x sub j over I not equal to j comes from. And then each polynomial is normalized at x sub I, so that q sub I of x sub I equals y sub I. So how do I normalize it? Well, I pretend that I've plugged in x sub I. This is the term that I want to survive. And so I need to make this first 1. So I divide by every term in the sum to make it go to 1. And then I multiply outside by y sub I to make it go to y sub I. So this thing goes to 1, and this survives. Okay, so this term, in conclusion, this term right here is the normalization term. So it sends it to 1. This term here is the vanish. This term makes the polynomial vanish at every other crucial point except for the specific xi that we were interested in. And then this term is the one that survives. Okay. And so then summing all these polynomials together, we get a perfect system that, every term in the sum vanishes except for the very one that we want it to. at that specific point. It's really a beautiful formula, and honestly, I wish I could do it more justice. I would love for you to check out some other YouTube videos on this topic and kind of convince yourselves that this really is a pretty wonderful idea that Lagrange came up with. All right, until next time.